All right, guys, so we're going to start in now on chapter 28, which is the first chapter of about two and a half chapters that we'll be covering that are about magnetic fields and magnetism. So we've learned quite a bit now about electricity, and now we're going to look at magnetism, which is a different, but as we'll see, connected phenomenon. So I want to start by thinking about, before we even get into magnetic fields, I want to think about where does magnetism come from? We know that magnets can create forces and fields, so we know that there are magnetic forces. You've all seen magnets attract and repel one another. And if there's a magnetic force, then there should also be a field. Right? Magnetism, like electricity, is what we call a field force. It's a force that is related to a field that exists in the space around something that creates the thing that creates the magnetic field, which is what I want to get into in this video now. So what creates this magnetic field? What is it? By comparison, I just want to remember that electric fields are created by stationary charges. So stationary charges, we know now, create electric fields. That's what we call electrostatic, stationary charges. And the simple connection is that moving charges will create magnetic fields. So that's the short answer here. What we're going to be thinking about here in this unit are moving charges, which then create these magnetic fields. It might be worth pausing for a moment. It's easy to imagine moving charges in terms of current through a wire, and that's where we're going to spend most of our time. And we're thinking about moving charges as electric current. If I have charges moving in a wire, that's an electric current. Those are moving charges that should create a magnetic field, and they do. But you're probably more familiar with what we call permanent magnets, which is, a hunk of metal that happens to create a magnetic field. We aren't really permanent magnets. A permanent magnet also creates a magnetic field. This is just a piece of metal that happens to somehow create a magnetic field. And you might be wondering, what are the moving charges in that hunk of metal? And I'm not going to go into this in this video in any great detail, but I'll just note that this is related in the moving charges inside a permanent magnet are related to electron motion in the material, in the metal. And there's a lot to be said there that I'm not going to get into, of course, because there are moving electrons in all materials, certainly all metals, but all materials you have moving electrons. So why is it that only some materials create magnetic fields? And furthermore, there's a deeper question about there are some materials that will create a magnetic field. Then there are other materials that don't create magnetic fields but will respond to a magnetic field. And then there's a third category of materials that don't even respond to magnetic fields. So there's a lot to get into there that I'm not going to get into in this video. We will ultimately spend most of our time dealing with electric currents, and that will be the bulk of chapter 29. What I'd like to do in this video is get back into this notion of what is a magnetic field and what are magnetic forces. Maybe the easiest way is actually to start by thinking about the magnetic force. Turns out that a magnetic force will be exerted on a moving charge. This is a force on a moving charge in a magnetic field. So let's imagine, for instance, that we have a magnetic field here. Here is the magnetic field directed this way. And for now, we'll just say it's just a uniform magnetic field. By the way, I haven't done this before, but B is our symbol for magnetic field. And let's imagine that I have a charge, Q. Here's plus Q right here. If this charge Q is in the magnetic field but not moving, it will experience no magnetic force. It has to be moving. And furthermore, it has to be moving such that there is a component of the velocity that is perpendicular to the magnetic field. So if the charge were to move, if I had a plus Q here, if that charge were moving in this direction, then there would be no force. But if the velocity has a component that is perpendicular, then there will be a magnetic force from the magnetic field on that moving charge. So you might be getting a hint here that, all right, so if there's something about perpendicular components between the magnetic field, which is a vector, and the velocity, which is a vector, that recalls or that might make you think of the cross product. And that is in fact true, that the magnetic force, we could write an equation for it. The magnetic force, is equal to the charge, Q, which is a scalar, times the cross product of V, the velocity vector, cross B. So this is our equation, which would then be equal to QVB sine theta in magnitude form. The magnitude, maybe I shouldn't write it that way. I think I should say that the magnitude of FB then would be equal to QVB sine theta, where theta then is the tail-to-tail angle between V and B. Of course, in the case where it's perpendicular, which in the case I drew up here, that appears to be perpendicular, then sine theta is just 1, so it's just QVB, which will then allow us to talk about the magnetic field. So by extension, in this case up here, then I could say that B is equal to, or the magnitude of B, maybe I'll just say the magnitude of B then is equal to the force divided by Q times V. And this then is one way of defining the magnetic field. And I think for our purposes right now, this is a good definition of the magnetic field. And it is similar to the way we defined the electric field. You may remember way back when we said that the electric field is equal to the force, the electric force on a charge divided by that charge. And this is similar. The only difference is rather than having a Q on the bottom, it's Q times V. And again, that's because whenever we're dealing with magnetism, we're dealing with moving charges. So you need the V term, which doesn't appear in the electric field equation. Let's go back and look at this cross product maybe a little bit and try to remember how cross products work in terms of vector direction. So if I wanted to know, for instance, in this case up here, if I wanted to know the direction of the magnetic force up here, if I had, again, B is pointed to the right and V is pointed to up, we need to use a right-hand rule. So I'm going to use the right-hand rule to find the direction of FB. Maybe I'll just go ahead and put a box around this, since that is an essential equation. So how does the right-hand rule work? There's several different ways of doing the right-hand rule. The way I'm going to sort of try to do it in this, I think the easiest way to do it in this medium is to draw your right hand. It's important that we use the right hand when we're doing the right-hand rule. So I'm going to take my right hand and I'm going to point my fingers, the fingers of my right hand, in the direction of B. So fingers go in the direction of B. Okay, and then I'm going to take the thumb of my right hand and point it perpendicular to my finger. So point it, in this case, straight up if it's my right hand. It's going to be like this. Here's my right hand. Thumb is in the direction of V. So fingers in the direction of B, thumb in the direction of V. And I think you'll see if you do that, that the only, if you're using your right hand, the only way to do this is for your palm to face in. So your palm is facing in. And the way we write into the page is with an X here, an X with a circle around it. This means in to the page, into page. And that then, the direction of your palm in this case is going to be the direction of FB. So all three are mutually perpendicular. You've got V, B, and F are all perpendicular. That's it. That's how the cross product works. B is the direction of the fingers. V is the direction of the thumb. And then your palm will show the direction of the force. You could, I'm realizing that's just an absolutely terrible picture of a hand, but I think you get the idea. I think you can see here that if we were to, those are my fingernails, maybe that, I don't know if that makes things any clearer, that this is the back of my hand, not the palm of my hand. But I think you could see that if we kept everything the same, but changed the direction of the magnetic field, if we made the direction of the magnetic field to the left, if you imagine keeping your thumb pointed upward, but moving your fingers pointing to the left. So now I'd have my thumb pointing upward and my fingers pointed to the left. Now your palm is facing outward. So now that what I would say here is your palm is facing outward, so FB would be outward. And the way we do outward is a circle with a dot, and that means out of the page. So again, this is B, that would be V, and so if I just changed the direction of B, then I would get the opposite direction, which is instead of into the page, it's out of the page. So that's just a quick reminder of how we deal with the cross product. One last thing I want to talk about in this video are magnetic field lines. So as with electric fields, we do draw field lines. So magnetic field lines. So I was drawing field lines up here. That's what these were, these blue lines. These were field lines, but I wasn't showing you where they were coming from. So let's imagine I have a magnet. Maybe for now, the simplest way to deal with this is to imagine that I have a magnet. And you'll remember that magnets have two poles. There's a north pole of the magnet and a south pole of the magnet. Do not call the poles positive and negative. There's a real temptation to kind of confuse electricity and magnetism. In electricity, the two opposite characteristics we call positive and negative. When we're dealing with magnetism, the two opposite characteristics are a north and a south pole. And they're given that name because, of course, the Earth itself is a magnet. So if I had the Earth, this in black, if I have the Earth and I took a magnetic needle, that needle, so if this is my magnetic needle, that needle will align itself so that one pole of the magnet, which on a compass needle is often painted red, one pole will point north. That's the north-seeking pole, and this is the south pole of the magnet, which points towards the south. So the north pole of the magnet points to the geographic north of the Earth. And the south pole of the magnetic needle points to the geographic south. And that's because Earth is a magnet. If you have two magnets, they align. So for that reason, we call the poles of a magnet north and south pole. Now, there's something tricky here that's a little bit strange, which is that as with electricity, the rule is that opposites attract and likes repel. So opposite poles attract, and like poles repel. You may have already learned this before. So opposite poles attract, like poles repel. So there's this weird thing in which what we call the geographic north pole, by extension, this has to be the magnetic south. Pole of the Earth. And what we call the geographic south pole of Earth has to be the magnetic north. Because the way the compass needle aligns itself, the north pole of the compass needle, this north pole is attracted to the magnetic south of Earth because opposite poles attract. And so that's a little bit, this makes things a little bit confusing or a little bit awkward, where what we call geographic north is actually the Earth's magnetic south pole, or they're not exactly in the same place, but they're relatively close. And what we call the geographic south pole of Earth is actually very near the Earth's magnetic north pole. So back to this magnet up here, we have this magnet and it's got these poles. So that means there's a field, there's something going on in space here, there's a field, and we can represent that field by drawing field lines. And by convention, we always draw the field lines going from the North Pole to the South Pole. So from north to south, north to south, north to south, north to south. So similar to how when we had electric fields, we said we will always draw the electric field lines going away from positives and towards negatives. Well, here we have the field lines are always going away from north poles and towards south poles. And what these field lines would show, we have to be a little bit careful about it. Remember, if I put a positive charge right here, the field line doesn't tell me the direction of the force on the positive charge, because if the charge is sitting there and not moving, there would be no force. And if the charge were, for instance, moving, let's say, in this direction, there would then be a force. But from the right-hand rule, you might be able to get a sense for the direction of the force here would actually be into the page. You can get that from the right-hand rule. So it's a little bit confusing what exactly these field lines are showing. But one thing we could say is if I put a compass needle here, let's say this is a compass, the north pole of that compass needle will point away from, will always point away from the North Pole and towards the South Pole, tangent to the field line, always. So if I were to put compass needle right here, the North Pole of that compass needle will point tangent to the field line at any point here. If I put it, maybe if I put one right here, I put one right here, again, pointed tangent to the field line, pointed in the direction of the South Pole and away from the North Pole. So these are magnetic field lines. They can be used to represent the magnetic field around a permanent magnet like this, a hunk of metal that happens to create a magnetic field, or charges that are moving due to an electric current. And we'll get to that when we get to chapter 29. But that's a quick primer on field lines, the magnetic force, and the magnetic field.